everyone? Mr. Geyser here with the second video in our Lesson 12A series, where we're taking a look at example 3 and 4, where first we'll be exploring and evaluating logs with the changing base. What I mean by change in base is we have this formula here that for every positive real number for a, b, and x, a being the base of the top log, b being a being the log base, x being what we were taking a log of, and b still being the base of the log that we want to take, where a cannot equal 0 and b still cannot equal 1. Regardless of the log that we're choosing here, what we're really doing is if we take the quotient of any log, so as long as they're the same log, log 5 of x divided by log 5 of 10 is equivalent to log base of 5 of x divided by log base of 10 of b. These two things, if x and b were the same, if we had a log base of 5 here and a log base of 10 here, we still get the same quotient. And that's also true for our natural log, where the log base b here, that b again just happens to be equal to e. Let's put this into practice with example 3. For example 3, we want to evaluate the log functions by changing the base of these logs here. For a, we're given log base 3 of 13, and theoretically, we could just put that into our calculator, but if we wanted to explicitly use and write out this property here, we're just describing that this log base of 3 of 13 is perfectly equivalent to log of 13, like a common log, divided by the common log of 13. Notice how the base now is in that bottom part of the fraction, and the 13 now is in that top part of the fraction. The denominator is for the base, the numerator is for the log, the term being logged. We can now just type that into our calculator, even dummy calculators like log of 13 divided by log of 3 is just going to give us that 2.335. Let's try that again for part B. In part B, we have that log base 6 of 10. That quotient is just going to be log of 10 divided by log of 6. And again, this log here doesn't need to be our common log. Theoretically, if we had some crazy situation where we were asked of log base 12 divided by log base 12 of 10 and of 6, it would still equal 1.285. Even though it's log base 10 in this example, even if it was log base 12, we would still get 1.285. In this case here, for part C, we're given log base 1/2 of 2, where this is exactly the same as the quotient of log of 2 and log of 1/2, which gives us that -1. And again, it doesn't matter what base we're using. Even if for all of these we happen to use natural log, we would still get the same value for all of them. The base, as long as it's the same in the numerator and the denominator of a x and b, the base that you originally started with, you'll still get the same values. Now, let's take a look at our next example. In example 4 here, we want to try and graph these logarithmic functions in this form of y equals log base b of some k value times x. We can show that the product property of y equaling log base b of k plus log base b of x is equivalent to some kind of vertical translation of the parent function, where a, the original parent function, is equal to log base b of k, just k, is equal to y equals a plus log base b of x. What I mean to say is, in example 4 here, we're given that we have our g of x is equal to log base 2 of 4x. First, what I want to try and do here is I just want to try and graph our parent function here. In part A, we want to use the product to show that it's a vertical translation of the function f of x equals log base 2 of x. In log base 2 of x here, we have our f of x going along this graph here. Now, for any log base like this, there are 3 distinct points that we are always able to graph. Notice how this log base follows that pattern of log base some number of x. When we have these logs, we know in our heart of hearts that the first point we can plot is that 1, 0. All logs of any number b pass through that point. The second point is this first one here, where we happen to have 1/2 divided by, 1/2, 1, -1, where really it's just 1 divided by the base, -1. The -1 persists, but it's that fraction that changes based on the base. That third and final point that changes based on the base exactly the same across all logs is this third point of b, 1, where our base is equal to 2, so we know that that third point there is 2, 1. But for part A here, what we're trying to explore is this g of x that equals log of 2 of 4x, where we can use that product rule to expand this log here to say log of 2 of 4 plus log of 2 of x. And really, I want to try and manipulate that log base 2 of 4 so it's some value. Now, I could use a calculator, but I could also be a bit clever and manipulate that 4 into saying it's 2 raised to the power of 2. I can take that 2 from the power, pull it out of the log, and now I'm saying 2 times log of 2 of 2, where any base of a log taking the log of that same base, so log base b of b, is just going to be equivalent to 1. So all I'm saying is 2 times 1 plus log base 2 of x, where really my g of x is just equivalent to 2 plus log base 2 of x. A bit of manipulation to try and showcase that this k value, that vertical dilation, really just is a vertical translation of some kind. Let's showcase this in part B, where we're going to graph both f of x and g of x on this grid to the right. Notice what happens to these 4 points here. They're all going to shift upwards 2 units based on this plus 2. Once we're given those 4 units there, we're able to graph out our actual grid here, where all we're trying to showcase is that this blue function line passes through those vertically translated points. And really, what we want to try and describe in part C is that g of x has a vertical translation of 2 units up. The horizontal dilation of 4 causes the same effect as a vertical translation in this case. Notice how this k value here really just is a horizontal dilation, where it's affecting our x value inside of our log. We should expect it to cause some horizontal dilation, but we end up getting a vertical translation, a shift upwards instead. Those two things happen to be perfectly equivalent. Now, in general, we could write this as a rule. I'm going to push everything over real quick. And the rule for this translation really is this f of x has x and y values, where it's being manipulated so that our g of x just has those same x values, comma, y values exactly the same, but plus 2. Thank you very much for joining me on this second video for our Lesson 12A series, where we explored some manipulation of our logarithmic functions, and we explored some of those properties where we expanded those logs in example 3. If you have any questions, please leave them in the comments down below, and I look forward to seeing all of you guys in class. Take care.